Hi, I'm Ethan, and I'm going to be talking about expected value. Aaron, I need to share my screen. Can you? Okay, okay, can you guys see the screen? Okay, well, I'll just get started. I think some of you may know what expected value is. It sometimes appears on AMCs, and it's a lot more common on other computational contests in the AME in addition. So basically, expected value in combinatorics is like when you have some kind of random variable and you want to find like the average occurrence of it. Like a lot of you have probably seen this before, but let's say you have a fair six-sided die, and you roll it, once. So what's the expected value of the number you roll? Well, you can roll 1, 2, 3, 4, 5, or 6, right? So then there's a 1/6 probability of rolling a 1 and a 1/6 probability of rolling a 2, and so on. So on average, your roll will be 1/6 times 1 plus 2 plus ... all the way to 6, and you can compute that this is equal to 3.5. So the expected value is like the average value that we expect to get when there is a random. And so what we can do with expected value is, first of all, we can look at we can look at another basic example, which is, let's say that we roll a fair coin. Sorry, not roll a fair coin. Let's say that we flip a fair coin a number of times, right? So on average, right, or what's the expected value of the number of flips it'll take for us to get heads for the first time? So the idea for this is that, okay, sorry. So maybe I should define expected value more precisely. So let's say we have a random variable x, right? And for now, we'll say it can take on some finite values, x1, x2. So x can take on values x1, x2, all the way to xn for some n. You can actually extend this definition to infinitely many values. But anyways, you have a random variable x, and it can equal any of these values x1 through xn. And the probability that it equals x1 is p1. The probability that it equals x2 is p2, and so on. And the probability that it equals xn is pn. So then the expected value of x, which I'll denote as E of x. I'm pretty sure this is the standard notation, is going to be equal to p1 x1 plus p2 x2 plus all the way to pn x. And the motivation for this definition is that it gives us what we think should be the average of x, right? The average value of this random variable x, because it'll attain this value x1 with probability p1, and it'll attain this probability x2 with probability p2, and it'll attain xn with probability pn. So we're essentially taking a weighted sum of possible values where the weights are the probabilities, and that'll give us an average value. So like this can be shown through like the example I just gave, where you roll a die. You can see that the average value is 3.5, right? Because the probability of rolling a 1 is the same as the probability of rolling a 6. Probability of rolling a 2 is the same as probability of rolling a 5, and the probability of rolling a 3 is the same as the probability of rolling a 4, right? So on average, right, your roll will be 3.5. And that's what we get when we do the expected value calculations, where the values are 1 through 6, and the probabilities are all 1, 6. So now we can apply this definition to do some more things. So first of all, let's look at another example. Let's say you roll flip a fair coin. Why did I do that? Why did I say that again? You flip a fair coin. So you get heads or tails, right? Each with 1/2 probability. And you flip that repeatedly until heads. You get heads. So what's the expected number of flips that you'll need to do? So on average, how many flips will it take you to get to your first head? So you could have 1 flip, which is H. You could have 2 flips, which would be you get tails and then heads. You could have 3 flips, and so on, right? And in general, if it takes n flips, you would have what? Let's see. There would be n minus 1 t's and then an h, right? And n can be any integer because you could have like really long strings of tails without a head. So what's the expected number of tails you get before you get to what's the expected number of flips you'll need to get to the first head? Well, let's consider the case where you'll need 1 flip. So this just happens with probability 1/2, right? 1/2 and then times 1. Okay, because the probability that you get getting 1 flip has probability 1/2, and then getting 2 flips has probability what? So 1/2 times 1/2, which is 1/4. 3 flips is the probability you get 3 flips is 1/8, because you need to get these 3s, and there's a 1/2 chance for each, and so on, right? The probability that you get n flips, we can see, is 1/2 to the n times n. Sorry, the probability that you get n flips that you need n flips is 1/2 to the n, and then you multiply that by n, because we're using the definition from earlier, where we're pretty much taking the average of all these occurrences and weighting them with the probability. So then we just need to find the sum of 1/2 to the n times n. And as you can So the way we compute this is, right, this is equal to what? This is equal to n times n. So we have 1/2 times 1, and then 1/4 times 2, and 1/8 times 3, and so on, right? So as you can see, we can like group these by the columns, where we have 1/2, 1/4, and 1/4. 2 times 1/4 is 3 times 1/8, or we can group them by rows like this. So this sum you can see is 1. This sum, again using the infinite geometric series formula, is 1/2. This sum is 1/4. And we can see that this too is a geometric series. So when we sum these, the expected value is 2. And that makes intuitive sense, right? If we flip a coin repeatedly, since the probability of getting heads and tails is both 1/2, we expect that like it'll take us 2 flips to get heads once. And now I'll introduce to you like a very, very useful idea in a lot of expected value problems, which is called linearity of expectation. So linearity of expectation. And this is pretty much like, the idea behind this is that in a combinatorial setting, we're just trying to change how we count things. And I think this is best illustrated through examples. For example, let's say we flip n coins, right? So what's the expected number of heads that we get? Well, if we flip n coins, right, we could consider, for example, how many sequences of n coins have 0 heads. So that would be 0 times. So we could consider the probability that a sequence of n coins has 0 heads, which would be n choose 0 times over 2 to the n times, right? So then times 0 when we compute the expected value, or if it has 1 head, times 1, and so on. We can keep doing this for 0, 1, all the way through n, right? But I mean, you might have noticed that there's like a much easier way to do this, which is just to consider each flip separately, right? What's the expected number of heads from this flip? Well, the expected number of heads from this flip is 1/2, right? Because there's the 1/2 probability that you get a head, and there's a 1/2 probability that you don't get any heads. So the expected probability for one flip is, the expected number of heads you get from one flip is 1/2, right? So that means you just sum the expected value for each flip. So then you get 1/2 times n as the expected value. So this example might have seemed kind of obvious, but the trick is that this idea of linearity of expectation, where we shift the way we count things, it works in situations where the events aren't independent. Like for example, what's an example? Well, the idea is that like, I'll give another example. For example, let's say that we wanted to, let's say we're given n coin flips, and we want to find the expected value of like pairs of consecutive things that are both heads, right? Now, but now in this case, the different events, which are different consecutive pairs, are not independent anymore. Because if these are both heads, that affects the probability that these are both, right? If we're given that these two are both heads, it's more likely that this and this are also both heads. So that means that these events aren't independent anymore. But the great thing about linearity of expectation is that it still holds even though the events aren't independent. So how many consecutive pairs are there if we have n flips? Well, we have one starting at the first flip, one starting at the second flip, and so on, all the way to one starting at flip n minus 1. So there's n minus 1 possible consecutive pairs, right? So there's n minus, and for each consecutive pair, on average, how many like HH, how many instances of 2 consecutive heads are we going to get? Well, obviously, right, there's a 1/4 probability that we get 2 consecutive heads, and there's a 3/4 probability that we don't get any consecutive heads. So for each consecutive pair, the probability we get 2 heads is 1. The expected number of pairs of 2 heads we get is 1/4. So then we can just sum this over all of the consecutive pairs, which there are n-1 of. So we get n-1 over 4 on average pairs that are equal. So the idea, this is kind of like, this is like really powerful because, again, we don't need the events to be independent. And if you were to try the other approach where you see where there's like 1 pair of consecutive heads or 2 pair of consecutive heads, it would be pretty much impossible for n greater than like 10, right? So now I'm gonna give a couple examples from competitions that kind of help illustrate the power of linearity of x. Oh, well, actually, no. Yeah, okay. So one example is from HMMT. I think this actually showed up on like Math Count's national countdown one year, but basically you have I'll just draw 5, but there's 2,000 chicks, sorry, 2,006 chicks in a circle, right? And so let's say at this instant, each one picks, so each one has one to the left of it and one to the right of it. So each chick picks one of the adjacent chicks at random, each with 1/2 probability to peck, right? So this will peck this one with 1/2 probability or this one with 1/2 probability. And so it'll pick one to peck with 1/2 probability. So what is the expected number of unpacked chicks? So remember, each chick randomly chooses one of its 2 neighbors to pack. So we want to find the expected number of unpacked chicks. So the idea is that we can just take each chick, find the probability that it's not pecked, and then like add up that probability for each chick. So for this chick, the probability that it's not pecked is what? Well, there's a 1/2 probability that it's not pecked by one neighbor, and there's a 1/2 probability that it's not pecked by the other neighbor. So there's a 1/2 probability, there's a 1/4 probability that it's not, right? So for this chick, the expected number of on average, this chick will not be pecked a quarter of the time. So that means on average, in total, we can just sum this probability up for all 2,000. So then we get, on average, we'll have 2,006 over 4 unpecked chicks, right? And like, again, this problem is another example. It's like impossible to do if you consider like, oh, how often will we have 1 unpecked chick? Or how often will we have 2 unpecked chicks? Or so on, right? So this is another example of kind of like the ridiculous power of linearity of expectation. And then finally, there's one final example I will show. Let's see. Which one should I do? Okay. Okay, yeah, let's do this problem. This is from CMIMC, I think. So let's suppose you have a 6-sided dice with 3 faces colored red, 2 colored blue, and 1 colored green. So you roll it 20 times and record the color that shows up on top. What's the expected value of the product of the number of red faces, blue faces, and green faces? So let's think about how we're going to do this, right? The idea behind this is kind of like, let's say, so one way of thinking about it is, let's say we have like, let's say that, well, let's consider this product R1. No, okay. The way we're going to do this is, let's consider what it means to take the product of the number of red, blue, and green faces, right? So we have, so let's say that we have these that are red and these that are blue and these that are green, right? So what does it mean to take the product of the number of red, blue, and green faces? Well, that means that we're just finding the number of triples, right? The number of red, blue, and green faces is just the number of triples of faces where one is red, one is blue, and one is green. So we're trying to find the expected number of triples of faces where one is red, one is blue. Sorry, we're trying to find the number of the average number of what are they called? The average number of rolls such that of triples of rolls such that one is red, one is blue, and one is green, right? So how do we do this? Well, well, if we're going to see on average how many triples are, whoops. Okay. So like I said, we're trying to find on average how many triples of rolls are there such that one is red, one is green, and one is blue. So how are we going to count that? Well, the idea here is that instead of looking at how many possible sequences of 20 rolls are there where the number of such triples is 1 or the number of such triples is 2 or so on. Instead, the way we can do this is we can consider each triple. So for example, we can have the first roll be red, the second roll be blue, the third be green, or the first one be red, the third be blue, or the fourth be green, or the fourth one be red, or the second one be blue, or the 19th be green, or the 15th be blue, sorry, or the 15th be red, the 7th be blue, and the 20th be green, right? So, or there's a lot of other possibilities, but we can consider for each triple, what's the probability that one is, so what's the probability that we get this one is red, this one is blue, and this one is blue, right? So the probability of this is obviously, well, the probability that this is red is 1/2. Probability that this is blue is 1/3. And the probability that this is green is 1/6, right? So that means that for each triple of distinct rolls, for example, 1, 2, 3, or 15, 17, 20, the probability that this one is red, this one is blue, and this one is, the probability that this is red, this is blue, and this is green is equal to 1/2 times 1/3 times 1/6, which is 1/36, right? And so that means we can just sum this over all the triples to find the average number of triples, which is the average value of the product. So the number of triples, well, there's 20 choices for which one is red, and then there's 19 choices for which one is blue, because it can't be the same as the red one, times 18 choices for which one is green, because it can't be the same as either the red or the blue. So that means there's 20 times 19 times 18 triples in total. And then on average, each of these triples is red, blue, and green, 1/36 of the time. So that means the average number of triples that works, which is equal to the expected value of the product, is equal to this, which you can see, you can get that this equals 109. So linearity of expectation is a kind of powerful idea where you like shift the perspective, right? Instead of counting how often this product equals 1 or how often this product equals 2 or whatever, you can instead shift your perspective to count something else, right? How often does this contribute to the product? So in the end, I'm going to leave you with a couple homework problem. Well, there's one homework problem and there's one problem that I think is fun and you should recommend, and I recommend that you do. So the first one is, so this is an HMMT problem, and you can solve this with an argument of like linearity. And the second one is an AMC problem, and it looks like long and intimidating, but like once you get past all the notation, you'll see that the argument is just like linear. Yeah, this one. This one was like uh, on the test, like I feel like the biggest factor with this problem is intimidation. Like if you actually read it and you think about it for some time and you're familiar with the idea of these kinds of linearity arguments, then like the solution is very natural. So I would recommend you do this one because I think it's very nice. And this is like our homework problem, this one. But I think the second one is also pretty interesting, and it's pretty instructive, and it'll give you a better grasp on like on this like honestly pretty overpowered combinatorial idea. So if there's any questions, yeah, you can ask now, or but otherwise, Sheldon can take it. Okay.